Welcome to another video. This is Easy Guide to Insulation Resistance, where hopefully we can cover how to carry out an insulation resistance test on any installation, and also how to fault find and what happens if you did leave something plugged in whilst testing. This is great for if you've got any exams coming up. What do we need to do? Well, this installation, every installation should be, before being put into service, should be inspected and tested so far as reasonably practicable. What does that basically mean? It means you should test it before you turn it on and make sure that it is in a fit working condition before energizing. So therefore do your dead tests. So which dead test do we actually do? Well, in this video we're going to do insulation resistance. So a small regulation, but one not to be ignored ever, because you should never actually damage the installation which you're about to test, especially as we're about to put 500 volts down the circuits. This regulation then tells us that we should carry out the test before energizing the circuit, and that all tests must be carried out in order, as suggested by the regulations here. So what does this regulation tell us? Well, the first regulation on here just basically tells us to test between live conductors and between live conductors and the protective conductor, but most importantly it says connected to the earthing system. Regulation 643.3.2 basically tells us to look at the table below, and basically telling us that we need to test our low voltage circuits at 500 volts, and the minimum insulation resistance should be 1 megaohm. Now what it does tell us is we should test every distribution board and distribution circuit with all electronic equipment removed. Therefore, it is important to remove all the equipment vulnerable to test, because what we would like to do is test every single circuit in that distribution board in one go, rather than keep disconnecting each circuit separately. So what sort of things could we have connected in? Well, surge protective devices, which are going to become more and more common if you aren't already seeing them now, they definitely cannot be tested and therefore may need to be disconnected from the circuit. RCBOs, obviously been around for years, they may not be able to be tested and you may damage them. New to the market, arc fault detection, and this here we have a Wilex, and this one has all three in one, so it's an arc fault detection, RCBO and circuit breaker, which obviously is the same thing. Dimmer circuits and anything dimmer switches needs to be removed, time clocks and also USB sockets. That bit of paper that you threw away when you're installing that equipment, you may need to read it, because it may well say "do not mega" is the information it may provide on it. So if we do have surge protection connected, then what we can actually do is lower the test voltage if you think that equipment is likely to influence the verification of the test, as this regulation says, or that you might damage it if you cannot remove it. So let's lower it to 250 volts. However, bear in mind that the minimum insulation resistance should still be at least 1 megaohm. Regulation 643.3, where the circuit includes electronic devices which are likely to influence the results or be damaged, suggests what we can do is we can connect live conductors together, remember that's line and neutral, and then test those two down to earth. Don't note, it does say additional precautions such as disconnection may be necessary to avoid damage to electronic devices, but remember, this is your responsibility. When it comes to the test sheet, we have two columns in particular, between live conductors and live conductors and earth, but we have a new one, insulation resistance test voltage, that allows us to record the test voltage for each circuit that we have been testing. But at the top of the form, as always, we have got details of circuits and or installed equipment vulnerable to damage when testing. This should record information for all the equipment that you're about to remove. Remember, think of future testers, or the future tester could be you. You'd be glad if people wrote it down. So here we're going to do an insulation resistance between line and neutral, 500 volts, and press the test button. But this time we get a reading, and we get a reading because we've got a neon in circuit, and this is what neons will do. They actually light up, so if you don't know where they are and they're in circuit, they will appear as a reading. You won't destroy it, but I can't say the same for any other electronic equipment that you may or may not forget that is installed in the circuit, which is why it's important to record it for future testers. So what would happen if you did test with equipment connected and you put 500 volts down it? Well, probably not a lot. Or then again, maybe it could. So what is insulation resistance? Well, basically it's making sure that the line and neutral are not touching, the line and earth is not touching, and the neutral and earth is not touching. So basically we're going to put a voltage through it, and the voltage we put through it is a nominal 500 volts. Now why 500 volts? Well, think about it logically, it's quite simple really. The voltage we're going to put through the circuit is 230 volts, and therefore we would like to test it at a higher voltage than actually passes through it. Now why 500 and not 300? Well, it comes back to the fact that 230 volts is an RMS voltage, and RMS is 0.707 of the sine wave. In other words, just to give you a rough idea, there's our sine wave, very badly drawn, very uneven, and our 230 volts is roughly there, 0.707, which is called, and you've probably heard it before, called the RMS. So actually 230 volts is here, but actually goes up a lot higher. In fact, what it actually peaks at is roughly 325 volts is what actually peaks, but it's there for such a small amount of period. So 0.707 is the RMS, because it's the same equivalent heating effect that a 230 volt DC supply would be. So therefore when we test it, we test at 500 volts, because that's higher than what goes in there. The analogy I always give, if people go test lifts and test cranes and things, what they do is they don't, if it's supposed to carry 8 people, they don't ask for 8 volunteers, they'll load it with whatever the maximum weight is, but they'll go beyond that maximum weight to test to see whether it actually carries it safely. So here is our circuit. We're going to test it at 500 volts, and we're testing between all live conductors and earth. As we've said, we remove all loads from the supply, so we don't want to test them, basically. So making sure everything is fixed back, nothing is connected, all switches are turned in the on position, and obviously power is isolated. This is a dead test. So what are we testing for? As the name suggests, insulation resistance. Now, insulation does have a resistance, it's just very high. Hence what we're looking for is anything in the mega ohms. In fact, more specifically than that, it's got to be higher than 1 mega ohm for individual circuits as a whole. So basically the way to look at it as a simple circuit is to look at it as that. So there is a circuit, and this resistor between the two relates to the insulation resistance. Okay, so it's going to be a big figure. So there's a lump of cable that you put in for a specific circuit, and let's say that comes out at 200 mega ohms. So that's basically what it would mean, is that you have 200 million ohms of resistance between the two. In other words, they're not touching, it's just insulation. Whereas if you get a dead short, as demonstrated, then dead short comes up as 0 ohms in this particular case. Now, a question that's often posed is, what happens if you double the length of this? So you've installed this circuit now, and then the client says, I'd like to double the length, or you want to add another socket, or whatever it happens to be. So you're going to join onto this cable, and you might put exactly the same cable on again. And the exact cable from that manufacturer will have an insulation resistance, which also, this particular section, is we have 2 lengths cable joined together. Basically what we've now got is parallel resistances. So in insulation resistance, the formula is a parallel resistance. It's that. Okay, so it becomes 1 over 200 plus 1 over 200 and 1 over your answer as well, equals, in this case, it'll be half of that. So with this installation, what you're basically going to end up with, if you double the length of these cables, what happens to insulation resistance is the insulation resistance comes down. Now the same is true, because what it would like you to do is test all your circuits in one go. So if these are all individual circuits as well, so that's circuit 1 and then a circuit 2, 3, 4, 5, 6, 7, and each one of them is 100 mega ohms each. When you test them collectively, they will reduce proportionally for the amount of cable you have installed. So that's a typical question that gets posed at any exam you may well do. What happens if certain circuits have insulation resistance and you test them collectively? Well, the overall resistance will come down, which is why the guidance, doesn't say it in the regs book, is the guidance when testing distribution boards is anything over 10 mega ohms is deemed to be relatively okay. when testing distribution boards. So anything under that, you should start investigating why, is the recommendation. So first things we do, get permission. Let's turn the board off before removing the front cover. So I've already checked my testers on approving unit. So we're going to go, see this side is going to be live because it's the incoming supply, so we can definitely prove our supply on here. So this is coming up as 230 volts. But we want to go on the output side to make sure that is dead. So we go line neutral, line earth, neutral earth, and then going to check on my proving unit again. If everything turns up to be 0 volts, apart from obviously on the proving unit, then we now know that this is safely isolated. But remember, incoming supply up here, that is still on. What we do need to do is turn all circuit breakers on, because as I've said before, we're going to test a whole lot in one go. I don't have any RCBOs in this particular board, so therefore nothing invulnerable to test. I've already been round the installation and taken out anything vulnerable to test, so such things as dimmers, okay, lamps we've already spoke about, but please have a look prior to doing it, because the last thing you want to do is destroy them. All the circuits are on, we now need the meter. So here we have our meter, we turn it on, we go to insulation resistance, and we want to select it for 500 volts, which is our minimum required for an LV circuit. Okay, remember this is a low voltage circuit, not an extra low voltage circuit, so that's anything above 50 volts AC or 120 volts DC, and we test at 500 volts is what is required. As before, what you should always do is just verify your meter, especially those people who are going to do exams and things like that. They'll probably be looking for it for you to make sure it all works, and for your own peace of mind and benefit, to make sure you're not wasting your time. So, leads apart, leads plugged in as appropriate, where they tell you to, or where the instructions of your particular meter tell you to. Press the button, and then this gives you an open circuit. So what we now know is that the voltage is okay, so the batteries must be okay, and it's greater than 500 mega ohms, my apologies, greater than 500 mega ohms is the insulation resistance between these 2 points. So that's what an open circuit would look like, okay, and that's a good value, it's obviously what we're after, just to make sure without electrocuting yourself. Okay, so that's fine, put that together. So this is a dead short, and a dead short now reads 0.0 mega ohms. So we now know what the two extremes of the meter do. There's no need to zero it. People bizarrely sometimes say they need to zero the leads. No, you don't. Okay, but then anyone who knows their stuff would know that anyway. So dead short, open circuit, meter works. So we have two columns to fill in our regs scheduler test results, live to live and live to earths. Okay, so it doesn't elaborate on what's what. Remember, line and neutral are both live conductors. So all switches turned on, and then we can actually go on either side because they're all switched on anyway. And live to live, I'll just go lines to neutrals in place and press the button. And then what we now do is we go around and press any two-way switching that you may have, or any switches that are already in the off position, make sure they're turned on obviously, and we go around and press the two-way switching and test again. Now we go round and we now test lines to earth, and remember, as it says in the regulations, it should be connected to the earthing system, so everything must be connected to the earth, to the installation itself. And then go around and operate the switches again. Make sure you're pressing all your two-ways and your intermediates, and all switches are turned on again. We can now test neutral to earth is the last one. Now, again, and unless you've got switching in the neutrals, and they need to be switched for a particular reason, that should be sufficient for that. And as you can see then, we've got greater than 500 for every single circuit. So now when we write it on the test sheet, that greater than 500 can now appear across every single circuit and every possible combination. So we've got 1.72 megaohms. Not a fail, but you might want to investigate that. As we're testing a group of circuits, we need to find out which circuit, further investigation requires which circuit may be at fault here. How do we find it? So what we can do is we can switch the breakers off. We don't need to disconnect anything, and which is always the best thing when doing testing. Try not to remove as much as possible. Leave it all intact. So what we need to do, we do know that the fault is between line and neutral. So all we need to do is test either one side or the other and find which circuit has got the fault on. So we can leave it on there. And I can press the test button. And it's going to be the last one, isn't it? And that's the one with the fault on. But we can just prove to make sure. Let's just check. So these all should be clear. So we now know the fault is in the circuit number 1, which was the shower. All we need to know now is find out where it is so we could break this circuit down, split the circuit. There's only be a few points on the shower circuit, the isolator, the shower itself. So test each section of that circuit and see which part of the circuit is at fault, and then replace it. So here's another fault. This time the fault is found to be between line and earth. So we can test every single circuit to earth, to the earthing system. So short circuit line to earth. And same procedure, turn each breaker off or turn them on, whichever is your preference. Oh, that's clear. So we'll just make sure it is that one. So I'm going to turn all the others back on. So that confirms that it is circuit number 2. And again, this is on a ring final circuit, so we need to break down the circuit between line and earth throughout that installation and find out which part of the circuit is at fault. First things first though, double check, make sure you've got nothing plugged in. So neutral to earth, and we've got 0, 0, 0, which means there's a dead short between neutral and earth. Unlike before, where we could turn the breakers off, we can't do that now. So what we need to do now is we need to take out these neutrals here. We can leave those intact, we don't need to touch those because it's neutral to earth, and so therefore we've got to go through these one at a time. Again, I'll start with number 6. And as luck would have it, that would give us a 0 on that particular one, but we can just check, make sure. I'll test all the others in place, so I don't need to do that one. So leave that one out, test all the others to earth. and they've all come greater than 500, so that's good.